Welcome to the Explainer, folks. I'm your instructor, and today we're jumping right into the essential source material for Domain 3 cryptography. We'll be uncovering the core symmetric algorithms and, honestly, more importantly, discovering the exact traps designed to trip you up on the CISSP exam. We're going to take these complex architectural concepts and distill them down into the precise, hard-hitting knowledge you need to succeed.
Okay, real quick, here's our syllabus for today. We're going to cover the core goals of cryptography, move into foundations and basic ciphers, explore the unbreakable one-time pad, compare symmetric versus asymmetric systems, break down algorithms and modes, and then finally wrap up with key management and lifecycle.
Let's jump right in with Section 1, the core goals of cryptography. So, imagine a lighthouse for a second. Cryptography acts exactly like that secure beacon. It guides and protects your data in motion as it travels across the wire, while also acting as a tower of defense for data sitting at rest and data actively in use. As a security professional, your due diligence actually requires evaluating vulnerabilities across all three of these distinct states.
Let's rapidly break down the CIA Triad Plus 1, starting with confidentiality. This is all about the preservation of secrecy against eavesdropping or unauthorized access. Whether your data is sitting idle on a hard drive, traversing some untrusted network, or actively being processed in memory, confidentiality ensures that if an attacker intercepts the data, they see absolutely nothing but scrambled, useless ciphertext. Next up is integrity. If this is working right, the recipient has absolute assurance that the message they received is mathematically identical to the message that was sent. This protects you not just from malicious hackers trying to, say, alter a financial transaction, but also from random, accidental transmission errors. We typically rely on encrypted message digests and hashing to lock this integrity down.
Then we've got authentication. This is the mechanism that proves a user or system is exactly who they claim to be, usually before we even think about exchanging private keys. A classic example here is a challenge response protocol. That's where a server asks a user to encrypt a specific random piece of data. If the user returns the correct ciphertext, well, they mathematically prove they hold the valid key.
And finally, non-repudiation. Now listen up, because here is a massive exam insight. This guarantee, this undeniable proof of origin, is only offered by asymmetric systems, never symmetric. If a user digitally signs a contract, they cannot legally or technically deny having sent it.
All right, moving right along to Section 2, Foundations and Basic Ciphers.
So, there's a really fundamental architectural difference in how we actually process data here. Block ciphers literally chew on large, fixed chunks of data, like 64-bit or 128-bit segments at a time. Stream ciphers, on the other hand, encrypt bit by bit, right on the fly. You absolutely have to know which category to deploy based on your specific network constraints.
Okay, you're going to want to lock this instructor rule into your memory right now. Confusion complicates the key-to-ciphertext relationship, while diffusion scatters a single plaintext change throughout the entire ciphertext block. Generally, substitution operations give us our confusion, while transposition, or rearranging the data, provides the diffusion. Together, they form an incredibly robust defense against cryptanalysis. Let's take those concepts to Section 3, the unbreakable one-time pad. We're talking about the Vernam cipher here, and it has some absolutely strict, non-negotiable rules. The key has to be randomly generated with 0 patterns, physically protected, used exactly one time and then immediately destroyed, and it must be at least as long as the message itself. If you break even one of those requirements, the impenetrable nature of the pad instantly collapses. It's a remarkably powerful tool, but logistically, it's a total nightmare, because securely distributing a key that is just as long as the message itself is tremendously difficult.
The absolute most crucial takeaway here is that true randomness is literally mandatory. Pseudo-randomness or reusing a key is an automatic, instant failure of the algorithm. Fun fact, historically, the US cracked the top-secret Soviet Veneno project specifically because the operators got lazy and reused key patterns. So, do not fall for an exam trap that tries to use a phrase from a book for a one-time pad. That's actually called a running key cipher, and it is highly vulnerable to attack.
Which brings us to a huge testing area, Section 4, Symmetric versus Asymmetric Cryptography.
This is basically the ultimate trade-off in the crypto world. Symmetric gives you blazing, incredible speed for bulk data, but it totally fails at key distribution and scalability.
Asymmetric, on the other hand, perfectly solves that scalability issue with public and private key pairs, but it completely sacrifices speed. That's exactly why modern systems use hybrid cryptography. We use asymmetric to securely share a secret key, and then switch to symmetric for the actual high-speed data transfer.
I really cannot stress this enough for your test. Same equals symmetric, and different equals asymmetric. Because both parties possess the exact same symmetric key, neither party can definitively prove who authored a specific encrypted message. If a test scenario requires non-repudiation or legal proof of origin, you have to immediately eliminate any symmetric-only options from your potential answers. Just cross them right out.
All right, let's dive into Section 5, Algorithms and Operating Modes.
You are going to want to take a mental screenshot of this matrix immediately. You absolutely must know the block and key sizes for AES, the legacy constraints of DES, and you need to remember that RC4 is uniquely a stream cipher. Also, notice how AES maintains a strict 128-bit block size regardless of the key length you choose. That is highly testable. 2 to the power of 256. Just think about that number for a second. This staggering figure represents the key space of AES 256. It perfectly demonstrates why modern cryptographic work functions make brute forcing mathematically unfeasible today. As an architect, you have to ensure your algorithm's work factor outlasts the actual time value of your data.
Watch out for the classic DES parity bit trap on the exam. DES specifies a 64-bit key, sure, but 8 of those bits are just for parity. So the true effective cryptographic strength of DES is only 56 bits. That's exactly why it was fundamentally broken and replaced. Even its stopgap successor, triple DES, is officially deprecated by NIST today and absolutely must not be selected for modern, forward-looking security architectures.
And finally, Section 6, Key Management and Lifecycle. So what happens when we need to recover an escrowed key? Like, say an employee suddenly leaves the company. Well, we never ever want a single person holding all the power to decrypt sensitive files. That's where M of N control comes in. We use split knowledge, where a minimum number M out of a total N agents must combine their pieces to unlock the data. For instance, you might need 3 out of 8 authorized agents to collaborate before you can restore the key.
Here is your ultimate due diligence requirement for the exam. Keeping the lock and the key in the exact same database is a totally catastrophic architectural failure. You're literally doing the attacker's job for them. For true enterprise-grade protection, you must leverage hardware security modules, or HSMs, to keep those keys mathematically secure and physically isolated.
I want to leave you with a final thought to really ponder for your future architectures. As quantum computing advances towards reality, will today's supposedly unbreakable 256-bit symmetric keys just become the easily broken ciphers of tomorrow? Cryptography is an ongoing arms race, folks, and the life cycle of secrecy never truly rests. Moore's law pretty much guarantees that computing power will only increase, meaning today's unbreakable cipher is tomorrow's textbook example of a weak key. You must constantly govern and update your cryptographic standards. Thanks for joining this explainer, stay sharp, and I'll catch you next time.